larynx, followed by the trachea branching off into two primary bronchi. When I think of the bronchial tree, I always include the trachea because I think of the trachea as the trunk of the tree. In this case, the bronchial tree is beginning at the bronchi, your primary bronchi. That's okay, whatever works for you. I personally see a tree. That's okay. So we have many bronchioles. Remember me telling you how we have the bronchi, and the primary bronchi branch into secondary bronchi or lobar bronchi, going to each of the lobes. And then we have the segmental bronchi going to regions within the lobes called segments. Beyond the segmental bronchi, we branch into bronchioles. So the segmental bronchi have cartilage in plate form. And then we go to bronchioles, and we don't bother naming the bronchioles because who's going to remember 65,000 bronchiole names? Yeah?
Do you care what we call the bronchi, whether it's primary or the lower?
Whatever works for you. You'll hear me kind of flip back and forth. I tend to go primary, secondary, tertiary. Right? First, second, third. But it makes a lot of sense that the secondary are lobar because they're going to each of the lobes. Mm-hmm. And it makes a lot of sense that the segmental is going to be within the lobes where we have segments. And the beautiful part about the segments is, as you can see here, they're independently ventilated, they're independently utilized, which means that if you have a tumor, or you have a problem with a particular region of your lung, who was it? Whose lung was your father? Yeah, so they took a segment of his lung rather than all of the lung, which is really definitely better than losing the whole lung. My father-in-law had mesothelioma. They tried desperately to take care of him. They removed that entire lung. Well, of course, that was the death knell, which of course mesothelioma is already, but it just hastened his demise, really. Okay, because it was horrible, horrible disease. Absolutely horrible. Interestingly enough, my mom died of mesothelioma too. She was in London during World War II. London was blitzed. Germany bombed London. Asbestos was big in the 40s, 50s, even into the 60s. They used a lot of asbestos in building construction and even in paint. So she inhaled all that asbestos, didn't know it until she was in her 80s. And then, pretty ugly. Never mind, I digress. All right, so we have these three regions of our bronchial tree. And remember that we have the cartilage of the bronchi. And remember that we have, of the segmental bronchi, 10 on the right and 8 on the left. I don't care that you name them, just know that we have segments and how many are on each side. And of course you're gonna have more on the right side because you have more lobes and segments on the right side. So another view of that breakdown. Here's there's our trachea, there's our carina, here's our two primary bronchi, and then this one isn't showing you the extent of your three bronchi from the right side. Weirdly enough, they've kind of done it here on this side. So don't look at this as if it's right and left, right? It's more about looking to see that the bronchi have, as they reduce in size, plates of cartilage and the reduction in the presence of that cartilage until we get to our terminal bronchioles and then our respiratory bronchioles. And why do we differentiate terminal from respiratory? Because this is respiratory zone, this is all conducting zone. Okay? We have the ability to constrict our bronchi, and we have the ability to dilate our bronchi, and that's really better done at the bronchial level than it is the bronchi level. Why? Because we have cartilage at the bronchi level, which kind of prevents us from really constricting forward like that. And that's the whole point of the cartilage, is so we don't have collapse of those tubes. So we maintain a patent airway down into our smaller bronchioles. And then down here we can control, right, the movement of gases back and forth. Mostly we want to increase the diameter, so the sympathetic nervous system is where we want to get more air in, more air out. We want to dilate our bronchioles, relaxing the smooth muscles surrounding them. Talked about that, right? It's a smooth muscle, sympathetic nervous system. You need to run away, you need to climb that tree, get away from the predator, or you're involved in a conflict, sympathetic system. And what do you need most? You need to make more ATP. What do you need to make the ATP? Oxygen. And glucose, of course. Yeah. So I think we've talked about all this, yes? Yeah. Yeah. All right. So get down into the respiratory division or the respiratory zone. Here we have our terminal bronchiole, and here we have our respiratory bronchiole, and the respiratory bronchiole leads to alveolar ducts. Alveolar ducts. And the alveolar ducts have around them and coming off of them alveoli. This is called an alveolar sac. This is an alveolar sac. Tube running down the middle. Alveoli pushing off of that tube, that alveolar duct. Each of these is a functional unit of the respiratory system. This is where diffusion occurs. This is where we move oxygen from the alveolus into the circulation, where we move CO2 from the circulation into the alveolus. Inspiration, bringing oxygen in. Expiration, moving CO2 out. What kind of epithelium forms the alveoli?
Simple squamous.
Simple squamous epithelium. Why simple squamous?
Easy diffusion.
Easy diffusion, right? We can only diffuse a molecule about 5 nanometers, 5 cells distance. So it behooves us to have a very short distance for that diffusion across what's called the respiratory membrane. Here, just a simple reminder, because oh my goodness, doesn't matter how many times I beat this horse, still somebody's going to get it wrong. Please don't. Remember that the blood that comes to the right heart is deoxygenated blood. It is going to be delivered from the right heart via the pulmonary trunk, carrying deoxygenated blood to pulmonary arteries, to the lungs. Those pulmonary arteries carrying that blood to the alveoli. Those arteries become capillary beds. Those capillary beds experience diffusion. From the pulmonary arteries, CO2 is diffused into the alveoli because it's in high concentration in the blood, low concentration in the alveolus. And that's what diffusion is, right? Down the concentration gradient. So that CO2 is going to diffuse from the blood into the alveolus. What's filling the alveolus in inspiration?
Oxygen.
Oxygen. So oxygen is going to be then delivered to that capillary bed because there's greater concentration of oxygen in the alveolus than in the blood. And then that diffusion of the alveolus, from the alveolus into the blood, back to the heart. Via what vessels?
Veins.
Pulmonary veins, carrying freshly oxygenated blood back to the heart. So we have many, many alveoli. Not all our alveoli are working. In fact, we have portions of our lung that we never access. You know those people that do that deep sea diving? They have the big, long fins, and they gulp air, and they gulp air, and they gulp air. What they're doing is reaching absolutely the deepest, most inaccessible portions of their lung and utilizing that so that they can dive deeper and deeper and deeper and still have an oxygen reserve. Because if you don't have an oxygen reserve, what are your neurons going to do?
Die.
They're going to die, and you only get 5 minutes without that. So they're forcing of deep, getting air forced down into the deepest recesses of the lungs. You and I, maybe we're using about half of our lung capacity sitting here right today. And we're not even utilizing all the oxygen. So we have red cells that are carrying oxygen, the coursing around, coursing around, coursing around. We call that the venous reserve. Remember that? Right? Get your oxygen reserve just in case for the 5 minutes. Yeah. So we have many, many alveoli. for that exchange of gases. Here's a nice close look at an alveolus made of squamous epithelial cells. And in between, in the middle of each of these alveoli, we have an alveolar pore. These pores are really essential because they allow the alveoli to equalize pressure among themselves. Pneumonia, you can see, would be problematic where you couldn't do that. So that would be making your breathing labored and much more difficult. So we have the alveolar cells that we call pneumocytes type 1 or alveolar cell type 1. I don't care if you call them alveolar or type 1 pneumocytes, whichever works for you, but know that they are the ones that form the alveolus. Then we have cells called pneumocytes or type 2 pneumocytes, and these type 2 pneumocytes are the ones that produce the surfactant. That's the fluid that allows for a reduction in surface tension, which then enhances the diffusion of gases. And then also that surfactant prevents the alveoli from sticking to each other. So it allows for slipping and sliding. So if you have a collapse of a lung, that surfactant prevents the sticking. Or even as your exhalation, if it's really forced, you're really pressing down on that lung material, lung tissue, you don't want those alveoli to stick together. So we have type 1 pneumocytes, type 2 pneumocytes. So these are the elements that form the alveolus itself, the squamous cells. Those type 2 are the cuboidals. And where are those type 2s? These are right there, little type 2, alveolar type 2 cell. And then we have these alveolar macrophages, as I said earlier, called dust cells. These guys are all around the inside of our alveoli, cruising around, making sure that no foreign proteins get into the circulation. They can also phagocytize small capillary clots, small blood clots. Yeah. So we depend on these alveoli because this is where the action happens. This is where diffusion of our gases occurs. We're going to be moving CO2 from the blood into the alveoli. We're going to be moving oxygen from the alveoli into the blood. And we're doing that on a regular basis. And every time we breathe in and out, we're diffusing gases one direction or the other. We have what's known as the respiratory membrane that involves the plasma membrane of the alveoli and the plasma membrane of the endothelium of the capillary beds, plus a basement membrane holding the two together. Remember that our capillary beds are lying over, very intimate to each alveolus. And the pressures are really important because the pressures are going to facilitate the diffusion. So we have greater pressure of CO2 in the blood than we do in the alveolus. Diffuses down its concentration gradient. We have greater pressure of oxygen in the alveolus than we do in the blood, and that will diffuse down its concentration gradient and hook up with our red blood cells. And our red blood cells, maybe you remember this, our red blood cells are really important in this process because they take up oxygen and hang on to it until they release it to the tissues. And what are the tissues producing? What's the waste product that's CO2?
CO2.
CO2, right? Tissues are producing CO2. And so the red blood cells now are free. They've given up their oxygen. Their hemoglobin is free to take up that CO2. But not all of that hemoglobin is going to hang on to the CO2. In fact, much of that hemoglobin is going to pick up hydrogen ions. Where does that hydrogen ion come from? CO2 plus water forms carbonic acid. Carbonic acid dissociates into bicarbonate hydrogen ions. That happens in the red cells because the red cells have an enzyme called carbonic anhydrase that binds carbon dioxide and water, makes the acid, and then that same enzyme dissociates the acid into bicarbonate and hydrogen ions. The hydrogen ions are then picked up by the hemoglobin. It's called deoxyhemoglobin. The hydrogen ions are kept in abeyance unless there's a lot of CO2. When there's excess CO2, there's only so much hemoglobin to take up that hydrogen. The rest of it is shipped off to the plasma, cerebrospinal fluid, medulla oblongata says, Breathe. Ventilate. You got too much, your pH is too low. So, it's based on pressures that drive this diffusion process. Here's the distance, right? 0.5 micrometers. Oh my goodness, it's a very short diffusion distance, but that's the extent of this membrane melding right here, which allows for that easy diffusion of gases. Pulmonary lead pressure is really low here. That is going to help with the lymphatic drainage and keep things moving and prevent fluid from building up in the alveoli. Lots of different tissues we've talked about, haven't we? So let's name some of the tissues we have in our respiratory system. We got epithelium. What kinds of epithelium do we have? Pseudostratified ciliate columnar.
Keratinized,
A little bit keratinized stratified squamous.
That's the word, right?
That's the one. Rolodex.
Simple squamous.
Simple squamous. Where? In the alveoli.
There's
What else?
cuboidal in the alveoli.
Got cuboidal in the alveoli. Yeah, because our type 2 pneumocytes. Cuboidal. Yeah, what else? What else? What else? I didn't hear it. What did you say, Gracie?
I accidentally said hyaline cartilage, but that's.
Hyaline cartilage, absolutely.
Oh, okay.
Oh, totally. It's like all the cartilage, except for
Epiglottis, which
the
is
epiglottis, which is elastic.
E.
Yeah, you got your hyaline cartilage septum, and hyaline is really prevalent in the body. So we got hyaline cartilage, we got elastic cartilage. What else?
Columnar.
Columnar epithelium.
Non-keratinized stratified squamous.
Non-keratinized stratified squamous. Do we have any ligaments? What are ligaments made of? Cartilage. No, ligaments are not cartilage. Ligaments are connective tissue.
Yeah.
Collagen. Lots of collagen. And elastin. So we have to have a little elastin. What else do we have? Oh, excuse me. We haven't mentioned the M word yet.
Smooth muscle.
Muscle. What kind of muscle? Smooth muscle. Where's that smooth muscle located? The trachealis is smooth muscle.
Bronchial.
All around the bronchioles, smooth muscle. We also have some skeletal muscle. Where's that? In the larynx, right? That's how we learn to speak, is to move those cartilages, open the glottis, close the glottis, so that we can vibrate those vocal cords by shoving air out. Every time we exhale, you are not speaking while you're inhaling. You are speaking while you exhale. The exhalation is forcing that air through the glottis and past those vocal cords, making those vocal cords vibrate. So that's great. And we'll pick this up when we get back to class next Monday. But what I just want to review this. Don't leave yet, just 1 second.